Welcome to Taylor series. So recall, we have seen Taylor polynomials. Of a function f at c. Which were defined as p sub n of x is the sum from k equals 0 to n of a sub n times x minus c raised to the n, where a sub n was equal to the nth derivative of f evaluated at c divided by n factorial. And we saw that as we added more terms, as we went to a higher degree, these approached f, right? So which approached f as n got large. So what we will do now is let that n go to infinity and look at the series. So we will now let n go to infinity. So definition for f infinitely differentiable, right? By which I mean you can take all derivatives. The Taylor series I'm going to say infinitely differentiable near x equals c. The Taylor series for f at x equals c is the sum from n equals 0 to infinity of a sub n times x minus c raised to the nth power, where a sub n is again that nth derivative of f evaluated at c divided by n factorial. Just like we had the Maclaurin polynomials, we also have the Maclaurin series. So when x equals c, sorry, not when x equals c, when c equals 0, we get the Maclaurin series. Which again is just the Taylor series with c equals 0, but essentially it's the sum from n equals 0 to infinity of a sub n times x to the n, where a sub n is simply the nth derivative of f evaluated at 0 divided by n factorial. So again, the Maclaurin series is just a particularly special Taylor series where our central point is x equals 0 instead of just a generic x equals c. So let's go ahead and do a quick example. Let's find the Maclaurin series for f of x equals e to the x. So note that the nth derivative of f evaluated at x is simply e to the x. We want the Maclaurin series. So we are looking at when c is equal to 0. So we need the nth derivative at 0. Well, that should simply be e to the 0th or 1 for all n. Right? So therefore, our a sub n's, which would be the nth derivative evaluated at 0, divided by n factorial, are simply 1 over n factorial. So we get that our Maclaurin series so the Maclaurin series for f of x equals e to the x is the sum from n equals 0 to infinity of a sub n is 1 over n factorial. And then Maclaurin series, we just do times x to the n. So this is how we could go about finding that Maclaurin series for e to the x. Now let's go ahead and try a Taylor series for f of x equals 1 over x, specifically at x equals 1. So again, note that f of x is simply x to the negative first power. F prime of x is a negative 1 times x to the negative second power. The second derivative would be a positive 2 times 1, which is just 2 factorial, times x to the negative third power. And in general, we actually get that the nth derivative of f is we have alternating signs, so we need a negative 1 to that. In this case, it's the odd power derivatives that are negative, so we should just do negative 1 to the n. Then we have times n factorial, right? Each time we take the derivative, we just add in that next, pull that power out front and just ups to the next factorial. And then times x to the negative, in parentheses, n plus 1. So what this means then is that if we take the nth derivative and we evaluate at 1, so here we're doing the Taylor series at x equals 1. So our c is 1. So our nth derivative evaluated at 1 would just be negative 1 to the n times n factorial. Putting all this together, we have that our a sub n's should be equal to the nth derivative evaluated at 1 divided by n factorial. But that is simply negative 1 to the n times n factorial divided by n factorial. And we just get negative 1 raised to the n. So we get for our Taylor series, so the Taylor series of f of x equals 1 over x at x equals 1 is the sum from n equals 0 to infinity of -1 raised to the nth power times x to the n. So just a quick question we could ask where this converges. A quick question. Where does this converge? Well, we can, for our radius of convergence, we can just look at the absolute value, right? So we can look at just the sum from n equals 0 to infinity of absolute value of x. Sorry, that shouldn't have been x. That should have been x minus 1. We were doing Taylor series. So we should have an x minus 1 to the n. I apologize for that mistake there. So we should be looking at now the absolute value of x minus 1 raised to the nth power. This is just a geometric series. So this converges for absolute value of x minus 1 being less than 1, and it diverges otherwise. And in fact, we don't even need the absolute values for this. In fact, we could just look at, in fact, the original series is simply equal to the sum from n equals 0 to infinity of -1 times x minus 1, that entire thing raised to the n, which is again a geometric series. And this converges again when absolute value of x minus 1 is less than 1 and diverges otherwise. So what we get is that our Taylor series, so the Taylor series converges on the interval from 0 to 2, and then otherwise diverges. So no matter how many terms we go out, it can only approximate 1 over x on that interval from, or only, the series only really converges on that interval from 0 to 2. So in the next video, we will take a look into, does the series converge to f? Is this Taylor series of f actually equal to f?